Hello. In this lecture, I am going to discuss the questions that appeared in the last CSIR JRF NET examination, that is September 2022 examination. Very specifically, I am going to discuss questions from statistical thermodynamics topic. Right. In the last examination, 4 questions were appeared from statistical thermodynamics. Question number 1. Let me read out the question first. For a system of 2 fermionic particles that can be in any one of the 3 possible quantum states each, the ratio of probability that 2 particles are in the same state to that when the 2 particles are in different states is. Okay, so in a system there are 2 fermionic particles are there. So question number 1. 2 fermionic particles are there. Okay, so system consists of fermions, right? And you know very well, fermions are of integer particles. Okay, of integer spin. Fermions are particles having half integer spin. Fermions are particles have half integer spin. Half integer spin means it may be 1 by 2, 3 by 2, 5 by 2, etc. Okay, so particles having half integer spin value are called fermions. Okay, examples for fermions, examples are electrons, protons, neutrons, etc., etc. Okay, these are all examples for fermions. Then fermions obey or follow Fermi-Dirac distribution or statistics. I repeat, fermions follow or obey Fermi-Dirac distribution. Okay, and according to Fermi-Dirac distribution, in a given quantum state we can place only one fermion. Okay, there is a restriction. Only one fermion can be placed in a quantum state. Why? Because Fermi-Dirac statistics are particles which obey Fermi-Dirac statistics follow Pauli principle. Okay, so for fermions, according to Pauli principle, if you exchange 2 identical fermions in a system, then the total wave function must be antisymmetric. Okay, so due to that condition, this restriction came actually. Only one fermion can be placed in a quantum state. Okay, now let me go to the question now. For a system of 2 fermions. Okay, so there are 2 fermions available now. 2 fermions, fermionic particles that can be in any one of the 3 possible quantum states. Okay, so there are 3 possible quantum states. Let us assume that the 3 states are degenerate. Okay, each line represents a quantum state, right? The ratio of the probability that 2 particles are in the same state. Okay, suppose I'll represent one particle with a star, another particle as another star. Okay, so what is the probability of finding probability for 2 particles in the same state to the probability that 2 particles in different state? Okay, just go through the line 3. The ratio, we need to find the ratio of probability that 2 particles are in the same state. For 2 particles to be in the same state, what is the probability? And 2 particles in different quantum state, what is the probability? Then take the ratio. Okay, they are asking the ratio. Okay, probability for 2 particles in the same state, 2 particles in the same state, okay, divided by probability for 2 particles in different state. This ratio we need to find out. And you know very well, according to Fermi-Dirac distribution, only one fermion can be placed in a quantum state. Okay, so probability for two fermions occupying a quantum state, okay, it is actually 0. It's not possible. So this probability is 0. Then in the denominator, whatever may be the probability, you will get some number, any number. 0 by something is 0 only, right? Okay, therefore this ratio should be equal to 0, right? So for question number 1, the correct option is C. Yeah, in option C we have 0, so the correct option for this question is C. Okay, it's a very simple question, right? They are asking the ratio of the probability for two particles in the same state to the probability for two particles in different state according to Fermi-Dirac distribution. Okay, only one fermion can be placed in a quantum state. So two fermions in one quantum state, that is not possible. So probability for this is 0. Okay, since the numerator is 0, whatever may be the denominator, so 0 by something is 0 only, right? So this ratio is 0. Okay, then now let me go to the question number 2. Let me read out the question first. Yeah. 6 distinguishable particles are distributed over 3 non-degenerate levels of energy 0, E and 2E. The most probable value for the total energy is, okay, see here, question number 2, what is actually given here is 6 distinguishable particles are given. Okay, so there are 6 distinguishable particles are given. Okay, and these particles are distributed in 3 non-degenerate levels of energy 0, E and 2E. So we have 3 non-degenerate levels. For this the energy is 0, for this the energy is E, and for this level the energy is 2E. Okay, and we have to distribute the 6 particles in these levels such that what they are asking, the most probable value for the total energy is. Okay, remember this point, this is very important. When we'll get the most probable distribution, the energy, the total energy correspond to the most probable distribution is what we call as most probable value for the total energy. Okay, so the most probable value for the total energy, this is what they are asking. What is the meaning for that? It is the total energy for the most probable distribution. Okay, which distribution is most probable? Keep this in mind. Whatever may be the case, okay, say if it is given 10 particle, 100 particle, whatever may be the case, if you distribute the particle in all the energy levels, in all the quantum states equally, that distribution is the most probable distribution. So we have 6 particles now, so place 2 particle here, 2 particle here and 2 particle here. That should be the most probable distribution. Distribute the particle equally in all the levels. Okay, so let me place 2 particle here. Okay, A and B. I am using the symbol A and B in order to distinguish the particles. That's all right. A, B, and another 2 particles C, D, and another 2 particles E and F. Okay, see, all these particles are identical particles. Okay, just for understanding purpose, I have given symbols like this, A, B, C, D and all. Okay, now these 2 particles are present in the level having energy 0. So what is the total energy? Total energy equal to, this is the most probable distribution. Keep this in mind. If you want to find most probable distribution, okay, here total energy is not mentioned. Okay, total energy is not mentioned. In that case, the most probable distribution is the one in which you have to distribute the particle equally in all the levels. If particles are distributed, okay, equally in all the levels, almost equally in all the levels, then that distribution can be called as the most probable distribution. So in this case we have 6 particles, so place 2 particles in each level. Okay, so you'll get the most probable distribution. What is the total energy for this distribution? total energy equal to, see here we have two particles. For this, energy is 0. Then in the next level again we have two particles. For this, the energy is E. Then the next level we have two particles having energy 2E. Okay, so what is the total energy? This is 0. This is 2 into E. This is 2 into 2, 4E. So total energy is 6E. This is the total energy for this system. So the most probable value for the total energy is 6E. Okay, for this question number 2. Okay, so the correct option for this question is option D. Right? Yeah. Now let me go to the next question. That is question number 3. Yeah. 1 mole of O216 gas and 1 mole of O218 gas, okay, are present in two different containers. 1 mole of O216 and 1 mole of O218 in two different containers of same volume have same entropy. Okay, so what is given? Let me write. Question number 3. This is question number 3. Okay, what is given is entropy for oxygen gas O2 gas with the isotopic mass 16, okay, and entropy for O2 gas with isotopic mass 18. Okay, these two entropies are equal. Okay, and volumes of the two gases are equal, and we have 1 mole of this gas and 1 mole of that gas. So number of moles equal, volume equal, entropies are also equal. Then assuming there are no rotational and vibrational contributions to the entropy, if the entropy of O216 is 300 Kelvin, if the temperature of O2 is 300 Kelvin, what is the temperature of O218? In Kelvin they are asking. Okay, if the temperature of this gas is 300 Kelvin, what is the temperature of this gas? So that the entropies of the two gases will be equal. Right, so we need to find out the temperature. How to do that? It's very simple. You know very well, internal entropy S is equal to internal energy by T, okay, plus Kb ln Q. This is the formula for entropy. Okay, you can use this direct formula to calculate the temperature. Okay, Q is system partition function, Kb Boltzmann constant, U is the internal energy at temperature T. Here we actually make an assumption here that internal energy at 0 Kelvin, okay, we assume it as 0. Under this assumption, entropy is given as U by T plus Kb ln Q. So what is U here? U is internal energy at temperature T. Okay, remember that. Now here in this problem it is given clearly that rotational and vibrational contributions, okay, are absent here, right? Assuming no rotational and vibrational contribution. So there is no rotational contribution to entropy, no rotational contribution to entropy, and no vibrational contribution to entropy. So it's very clear that is. So what we get from this is that only translational motion contribute in entropy, right? Therefore only translational motion contributes in entropy of the gas. Okay, so keep this point in mind. Right, now I'll make one more assumption here. Let us assume that the two gases are ideal gases. Okay, let us assume like that. Therefore, see what is given here, entropy of O216, entropy of O218 are equal, right? So let me take this point here. Now listen carefully. Entropy formula is U by T. So I'll keep 1 by T as such. Okay, what is U? if you assume the gas is ideal gas, then entropy is given as entropy equal to let us assume there are n molecules present, n into 3 into half kBt. Why I am writing this? See, half kBt is the energy for one translational degree of freedom for one particle. I repeat, what is half kBt? Half kBt is the energy for translational energy for 1 degree of freedom for one particle. If you multiply this by 3, you will get translation energy for 3 degrees of freedom, because each particle in a vessel has 3 different degrees of freedom. So 3 into half kBt is the contribution of energy of one particle into n will give you total energy. That is nothing but internal energy of the system. Okay, now plus we have this kb ln q. In the place of q, I'll put translational partition function, because only translation is contributing now. Translation partition function. Since we are taking gas here, in gaseous state the particles are indistinguishable. Okay, since we have assumed the gas as ideal gas, I can write system partition function in terms of single particle partition function. So qt is the single particle translation partition function, power n over n factorial. Okay, so this left hand side corresponds to O2 16. Keep that in mind. And what about in the right hand side? I am going to write the similar expression here, because entropies are equal, 1 by T into, since the amount of gas is 1 mole, number of particle also same, into 3 into half kBt. Let me write this as such, plus this term kb ln q translation power n by n factorial. Okay, I'm sorry, this square bracket will come in the numerator only. Yeah, denominator, there is no bracket in the denominator. Okay, I'm sorry. Now see, this left hand side and this, and the first term in the left hand side and the first term in the right hand side are equal. Okay, why are they equal? Because this t and this t cancel. Similarly here, this t and this t cancel. So now number of moles, since both the gases are 1 mole of gases are present, so number of particle in both the gas are equal. So n values are same, 3 by 2 kb, 3 by 2 kb, everything is same. So I can cancel this first term and this first term. Okay, then what we left with, let me write here kb into let me write this as with the formula a by b. So q translation power n minus ln n factorial. Similarly in the right hand side, kb into ln q translation power n minus ln n factorial. Okay, kb you can cancel, right? And here see, we have minus ln n factorial. Here also we have minus ln n factorial. I can cancel those two also, because number of particles are same. So let me cancel this quantity and this quantity. See, by the way that I wrote, the two expression look same. Okay, but actually this is translation partition function for O2 16 and this is translation partition function for O2 18. Clear? Now let me continue this. It's actually very simple, but you have to write with a few more steps, that's all. Okay, yeah, let me continue here. Now listen. So if I apply logarithmic rule, I'll get n into ln qt. What is translation partition function? Formula 2 pi m kbt whole power 3 by 2 by h cube into volume. Similarly here, n into ln 2 pi m kbt whole power 3 by 2 by h cube into v. Okay, yeah. by h cube into v. Okay, logarithm is applicable for all the three terms here. Okay, now I can cancel this n because number of particles are same. Okay, then we can also separate this further as, let me write here, ln 2 pi kb power 3 by 2 by h cube into v. I'll keep this term as such, plus this mass and temperature I'll write separately, ln m into t whole power 3 by 2. I can separate because they are all in multiplication, they are all exist with the multiplication, so by applying logarithm we can separate. Similarly, in the right hand side I can separate this as ln 2 pi m, not m, 2 pi kb power 3 by 2 by h cube into v plus ln m t whole power 3 by 2. Now these two terms are one and the same because volumes are equal. Okay, volume of the O2 gas and O2 16, O2 18 are equal, so I can cancel these two terms. Then what we left with is ln m into t whole power 3 by 2. Similarly here ln m into t whole power 3 by 2. Remember, here m is the mass of O2 16 molecule. Here m is the mass of O2 18 molecule. Here temperature is 300 Kelvin. Okay, we need to find out the temperature for O2 18. Clear? Now, if I remove log both sides, I'll get m into m. What is m? Mass of O2 16. Mass of O2 16 is 32. 16 plus 16, 32. Into temperature for O2 16 is given 300 whole power 3 by 2 equal to this side mass of O2 18. 18 plus 18, 36. Into temperature we need to find out whole power 3 by 2. Since the powers are equal, I can cancel the powers also. Okay, so what is T here? T is equal to 32 into 300 by 36. Okay, so 16 2s are 32, 18 2s are 36, 8 2s are 16, 9 2s are 18, then 1 3s are 300, 3 3s are 9. So 8 into 100 is 800 by 3. 800 by 3, 8 by 3, if we divide, you'll get 2. 2 to 6, balance to 20. In 20, we have 6 3. 6 3s are 18, balance to 20. 6 3s are 18. Point 20 again, so 6 6, like that it goes. This is the temperature. This is the temperature of O2 18. O2 18 gas, such that so that the entropy of O2 18 and the entropy of O2 16 are equal. Okay, if the temperature for O2 18 is 266.66, then only the entropy of O2 16 and entropy of O2 18 become equal. Okay, yeah, keep that in mind. So for this question, what is the correct option? Yeah, the correct option is C. Correct option is C, note down. Very simple, but we have to make some assumption here, that is the gases are ideal gases. Okay, by making that assumption we can calculate the temperature. Then let me go to the next question. Question number 4. Partition function. Question number 4. Partition function for a gas is given by, okay, they have given a partition function Q. Capital Q represents system partition function, which depends on number of particle, volume and temperature. It is given as 1 by n factorial into 2 pi m divided by h square beta whole power 3n by 2 into volume minus n into n, number of particle, n into b whole power n, and there is one more term into e to the power beta a n square by v. So this is the expression for system partition function given here, and what they are asking, the internal energy of the gases. Okay, yeah, how to calculate? Yes, you know very well, internal energy, let me write here, internal energy, the formula for internal energy is given as internal energy at any temperature T is equal to kB T square, and we are making an assumption here, keep that in mind, internal energy at 0 Kelvin is 0. Okay, this is the usual assumption, so we are making that. Internal energy at temperature T is equal to kB T square into dou ln Q by dou T, okay, at constant number of particle and constant volume. So by keeping number of particle and number of volume of the system constant, you differentiate ln Q with respect to temperature. Then substitute that value here, you will get the internal energy. Clear? So what I'm going to do, first I'll take logarithm for this equation. So ln Q is equal to, I'll take logarithm. So while taking logarithm, since n and v are constant, what I'm going to do, I'm going to keep the temperature term alone separately. So what I'm going to do first, okay, instead of doing ln Q, let me rewrite this Q in a different manner. Q is equal to, see here, I'll keep 1 by n factorial as such. What is actually beta? In statistical thermodynamics, you may be knowing that beta is nothing but 1 by kB into T. I'll substitute this value here. So if I put 1 by kBT, kBT will go to the numerator. So we'll get 2 pi m kBT by h square whole power 3n by 2 into v minus n into b whole power n into e power, in the place of beta I'll put 1 by kBT here. So a n square by v into kb into t. Okay, so I wrote the same expression Q in terms of temperature now. I replaced beta into 1 by kBT. Clear? Now what I'm going to do is that I'll take logarithm first. I'm going to take logarithm in such a manner that I'm going to keep temperature term alone separately. Okay, yes, how to do that? Very simple. Since all are in multiplication terms, okay, this 1 by n factorial 2 pi m kb by h square, okay, I'll keep them as such. Okay, so ln of 1 by n factorial into 2 pi m kb by h square whole power 3n by 2. I'll keep this as such. I'll just remove the temperature term alone plus ln, because it is in multiplication I can separate, ln t power 3n by 2, then plus here we have ln v minus nb whole power n. I'll keep this term as such. Then plus ln of e. Okay, if you apply ln to the exponential term, what will happen? Only the power term will remain. Okay, so just write here a n square by v into kBT. Okay, if you take logarithm for any exponential term, only the power term remains. All other term become 1. Okay. Now, see, here we have temperature term, here we have temperature term, and here we have temperature term. All other terms are temperature independent terms. Okay, we are going to make those terms as constant. So what I'm going to do, I'm going to differentiate this now. So dou ln Q by dou T, keeping number of particle and total volume constant, is equal to, the first term becomes 0 because there is no temperature here, plus what about the second term? First I'll apply logarithmic rule, so 3n by 2 will come front. Then we have ln t. If I differentiate ln t, I'll get 1 by t. Plus what about the third term? Third term, there is no temperature here, volume and number of particles are constant, so if you differentiate, that term become also 0. Then let me come to the fourth term. Here we have temperature in the denominator, so we have 1 by t. If I differentiate 1 by t, I'll get minus 1 by t square. So this plus become minus a n square by v kb, t become t square. So we get this after differentiation. Okay, let me rewrite this, the next page. So what we get here is dou ln q by dou t at constant number of particle and constant volume equal to 3n by 2t, 3n by 2t here, minus a n square by v into kb into t square. Right? So this is the expression for dou ln q by dou t at constant number of particle and at constant volume. Now I'll plug this value for internal energy formula. In the internal energy formula, okay, I'm going to put this value here. So what we get is internal energy. So internal energy at temperature T is equal to, therefore internal energy at temperature T is equal to kb into t square into this value. Okay, that is 3n by 2t minus a n square over v into kb into t square. Now I'll multiply kb t square inside. So what we'll get, in numerator we'll get t square, denominator we have t, so 1t, and in t square if we cancel 1t, you'll get 1t remains there. So you'll get 3 by 2 n, you'll get kb, 3 by 2 n kb t. Okay, minus here, if you multiply here, kb t square cancel, so we left with a n square by v term. Okay, so this is the internal energy of that gas. Internal energy of that gas. So check the options now. The correct option for this question is 3 by 2 n kbt minus a n square by v. Yes, option C. The correct option for this question is option C. Okay, yeah, it's a very simple one. Okay, just go through this lecture 2 or 3 times so that you'll get some clarity on how to find the internal energy, okay, and what's the expression for entropy, right? What is meant by fermions. Okay, you can learn some informations about the basics of statistical thermodynamics. Yeah. Okay, I stop here. We'll continue this with a few more questions from September 2022 question paper. Thank you.